Hi Precalculus. So we've been talking about one-to-one functions and their inverses, and I wanted to go over just a couple of definitions for you. So the first one is the definition of a one-to-one function. A function is one-to-one if no two inputs have the same output. Now one way we can look at this is with a mapping diagram. So if I have a function f that's mapping some points from the domain to the range, I might map 4 to 10, 3 to 7, and 1 to 2. In this situation, this is a one-to-one function because each input is being mapped to one output, 1 to 1. Okay. Now G, if I look over here, I've got the same points, 4, 3, 1 in my domain, and I have 10 and 7 in the range. It would not be one-to-one if I mapped one of my outputs to 10 and then I mapped another 1 to 10. Okay. In this case, this would be 2 to 1 because I'm mapping two things to one thing. So this would be an example of not one-to-one. Okay. Now, seeing this as a mapping diagram makes it really easy to understand, but generally we don't look at mapping diagrams. Usually we consider things as graphs or as XY tables. So the horizontal line test becomes a way to decide whether a function is one-to-one or not. Okay. So a function is one-to-one if and only if no horizontal line intersects the graph more than once. So some examples of this. If I had the graph of x cubed, any horizontal line I draw on the graph of x cubed only hits the graph once. So this passes the horizontal line test, which means it is one-to-one. Okay. Now if I look at the graph of f of x equals x squared, in this case, it hits the graph twice, and so this fails the horizontal line test, so it's not one-to-one. Okay. Now, I have f of x equals x squared again here because when graphs are not one-to-one, we can restrict the domain. So in your notes, write restrict domain. And what this does is it's going to cut off part of the function and it'll allow us to create a one-to-one function even though it's not originally. And so the way that you do that is on this graph of my parabola, what I don't want is the second half of the parabola. I want to cut off one of the sides. And so the way that I'm going to do that is I'm going to say let x be greater than or equal to 0. In that situation, I'm only graphing the positive half, or the part of the parabola where x is bigger than 0. And so now that I've restricted the domain, this function passes the HLT, which means it is one-to-one. Okay. So this is a trick on functions that don't pass the HLT. You can restrict the domain and then it will pass. Now the reason we care about this, functions have to be one-to-one for the inverse to be a function. So in finding inverses, we really only care about inverses of functions that are one-to-one. And so this is sort of a general test that you want to do before you actually go through the process of finding the inverse. That being said, how do we find an inverse? Well, if we have a function, f of x equals x to the fifth minus 3 over 2, the first thing you should do is double check and make sure that it's one-to-one. So I've got some random stuff on my calculator. I'm going to hit second plus 712 to just set the RAM back to 0, or back to default. I'm going to plug my function in. So the top half of this fraction is x to the fifth minus 3 divided by 2. Notice I'm putting parentheses around the whole top of the fraction there to tell it that it's all in the numerator. And now I graph it. And I see by the graph that this function is one-to-one, so I don't have to do anything with the domain. Okay. So now finding its inverse algebraically. The first thing you're going to do is switch x and y. So instead of f of x being a y, I'm now going to write x equals y to the fifth minus 3 over 2. So step 1, switch x and y. The second thing you're going to do if you're solving this algebraically is you're going to solve for y. And when you solve for y, because you're solving, we're going to be using SADMAP. So we're going to be using reverse order of operations here. When I do that, there's a hidden set of parentheses on the top of the fraction, just like the calculator had to have those parentheses. Okay. So when I'm deciding what to do first, I would say, can I subtract anything from both sides? Well, no. Can I add? No. Can I divide? No. multiply is going to be the first thing I get to. I want to get rid of this 2, so I multiply both sides by 2, and that cancels. Now I have 2x equals y to the 5th minus 3. Okay, this is still in parentheses, technically. There's nothing I can do with the exponent because the exponent is locked inside the parentheses, and then I get to the parentheses. Once you get to your parentheses, you start SADMAP all over again. So then I go back to the start. Can I subtract? No. Can I add something to both sides to help? Yes. I can add 3. So I get 2x plus 3 equals y to the 5th. And now I get to my exponent, so I'm going to 5th root both sides to cancel out my 5th power. And I get that my inverse function algebraically is the 5th root of 2x plus 3. Okay. So let's see, switch x and y, solve for y, and then the last thing is to rewrite using your inverse notation, which is f inverse of x. Note here, f to the negative 1 of x means inverse. It does not mean 1 over f of x. Okay, so this is bad. It does not mean 1 over. This is not the same thing as to the negative first power. It's just a special notation that tells you that this is the inverse. Okay, and I know that's kind of confusing because they use that negative 1 and it looks like a power, but it's not. Now, using the same function, we can also find the inverse numerically, and this is important. Sometimes when you try and do it algebraically, you're going to get stuck and you're not going to be able to find the inverse. Numerically means finding it with a table. So if I have x and f of x, or x and y, I could plug these values into my graphing calculator just like I did before. I've got this in my y equals. Okay, we're using the same function. And then I could go into my table, and I'm just going to include a couple of positives and a couple negatives. So negative 2 is negative 17.5, negative 1 is negative 2, 0 is negative 1.5, 1 is negative 1, 2 is 14.5. Okay. Here's my regular function represented numerically in a table. My inverse function is just the same table, but with the x's and the y's switched, because with an inverse, you switch the x and the y. So that would mean that my x would be negative 17.5, my y would be negative 2, my x would be negative 2, negative 1, negative 1.5, 0, negative 1, 1, 14.5, and 2. Now to check and make sure that this actually does work this way, if I go into my y equals, I clear this out, and I put my algebraic expression that I found for my inverse, recall the 5th root is the same thing as the 1/5 power. Okay, so on my graphing calculator, I can either type this in as 2x plus 3 to the 1/5 power, making sure that I put parentheses around the 1/5 power here. Or I can also hit the math button right here. If you hit the math button on your TIs, there's going to be an option here for an x root. If you hit enter on that, you can tell it the 5th root of 2x plus 3. Now if I go into my table, let's see the whole number. So if I go to negative 2, I have negative 1, negative 2, negative 1. If I wanted to see one of these 0.5s, like negative 17.5, what you could do is go into your table set, so second window or second table set, and start your table at the value you wanted to see. So negative 17.5 is where I want to start it. And then if I go on my table, there's negative 17.5 and negative 2. Numerically, we won't do this very often, but it is a really nice way to check and see if you actually got the inverse correct when you did it algebraically. Okay. And then last but not least, we could also find an inverse graphically. Now, inverses and their functions are symmetric over the line y equals x, because this is the only line when I switch my x and y points that I get the same value. So if I were to go back into my graphing calculator and I were to plug in the original function, so x to the 5th minus 3 divided by 2, and I were to graph both of these, I would get one curve, this is my inverse curve. I would get my other curve, this is my actual function. And now, to make it a little more obvious, I'm going to go ahead and graph the line y equals x, and I'm going to make this line be a dotted line. There we go. You can make it like that. And I'm also going to hit zoom and square to make my pixels be square. That way it'll be a little more obvious that it's actually symmetric. So there's my inverse function. There's my original function. They're looking more symmetric. Oh, that's weird. And there's a floating bubble that's the line y equals x. That's not what I really wanted. I'm going to go back one more time just for kicks. And instead of having this be a weird floating bubble, there's a dotted line. And for your notes, for the purposes of your notes, let's go ahead and sketch this. So here's the line y equals x. The inverse function looked something like that guy, and the actual function looked something like that. So here's my f of x, and here's my f inverse, and they're symmetric over the line y equals x. Alright, that's it for notes. We'll do practice problems in class, and maybe I'll post some later, but as of right now, there's no practice problems with this video. Hope you have a good night. Thanks, guys.